This video lesson is for Chapter 3, Part 1, Energy Efficiency. 3,850,000 times 10 to the power of 18 joules. That's the amount of energy the Earth receives from the Sun every year. The Sun provided the Earth, just last year, with more energy in 1 hour than the energy all humans consume in 1 year. Yet, we have huge energy production and consumption problems. Why is that? Well, for example, with solar panels, all the panels we build are not 100% efficient, meaning that some of the energy from the sun that enters a solar panel will be transformed in other energies that we don't need, for example, heat. So our machines are not able to transform the energy completely into electricity. First, we can define energy. Energy is the ability to do work or effect a change, and work is being done when something is moving. So there's basically energy involved every time we see something that changes speed or that slows down or something changing shape or changing state. That's where energy is involved. And the units of measurement for energy, well, the most popular ones are the joules. So we're going to use capital J for that one. Kilowatt hour, this one is used by Hydro-Québec when they bill your parents every month or so. So that's kW.h, and calories when we talk about food, for example. Here's a list of the most important forms of energy. Electrical energy is the movement of electrons, like in a battery or a generator. That's why there is electricity. Electrons are in motion. Thermal energy has to do with when it's hot or cold, and it has to do with the motion of particles. Like in a fire or a hot plate, the particles move a lot, but in an ice cube, the particles move less, so it's colder. Radiation energy comes from the electromagnetic waves. Like in cell phones, you have Wi-Fi, or radio waves in a radio, they all work with the same types of waves. It's radiation energy. Chemical energy is stored in chemical bonds. For example, in fossil fuels, they are made of large molecules. When you break up the molecules, that's when we burn them, you get a lot of energy out of this. Wind energy is the movement of air, and we can use it with wind turbines to transform wind energy into electrical energy. Sound energy comes from sound waves, which are mechanical waves that need to travel in a certain medium, like through air or through water. So any sound or music can be looked at as energy. Hydraulic energy comes from the movement of water, like in a waterfall or in currents. And in Quebec, we use that to transform hydraulic energy into electrical energy in a hydroelectric dam. And nuclear energy is stored in the atomic nuclei. So that's the bonds of the protons and neutrons in the nuclei of all atoms. And the stars also run on that type of energy. And there's this very important law that describes everything we have observed about energy. It's called the law of conservation of energy. And the law states that energy can be neither created nor destroyed. It can only be transferred or transformed. That means we cannot make energy appear out of nowhere. We have to use energies that already exist in nature, and we can only transform them into the energy we want. For example, we can use sunlight, which is energy, and transform it into chemical energy. That's when we grow food, like when we grow carrots here. Or if you want, you can transform electrical energy into thermal energy, but we cannot create thermal energy. It has to come from another kind of energy. We can also transport energy from one place to another. And in an isolated system, so that's if you imagine you had a perfect thermos cup, the total amount of energy is always the same in that perfect thermos cup because nothing can exit the cup and nothing can enter it. So an energy transfer is the movement of energy from one place to another, and the energy remains the same type. On this diagram, here, after we have electricity, When electricity travels on the wires, it travels very long distances, but it's always the same type. It's always electrical energy. So that's an energy transfer. There are also energy transformations, which is the change of energy from one type to another. So I can look at fossil fuels at the gas pump, at a gas station. It's a liquid we put in a car. That liquid contains large molecules full of chemical bonds. Inside the car's engine, we burn those molecules, producing movement, so mechanical energy, also heat, so thermal energy. So that's a transformation, one type to another. Now we're going to explain how to calculate energy efficiency. Being efficient usually means that you use everything you have. So you use all of your time, or you use all of the energy you have. And energy efficiency is actually a percentage of energy consumed by a machine that was transformed into useful energy. So it's a comparison between the consumed energy, that's what goes in a machine, it's what enters the machine, versus the useful energy, that's what exits the machine. So the formula goes like this. Energy efficiency is the amount of useful energy, so that's what is going to exit the machine. It's your final kind of energy, divided by the amount of consumed energy, that's what's going to enter the machine. And multiply that by 100 to get your percentage. In that formula, all values of energy are given in joules, capital J. And instead of writing this long formula every time, we're going to simplify it to EE, energy efficiency, equals EU, useful energy, divided by EC, consumed energy. This slide is to help you visualize the difference between useful energy and consumed energy. In a car, we have to put in gasoline, so that's our consumed energy. A car consumes energy, so the gasoline is chemical energy. It's consumed, it enters the car. The goal of a car is to move, so you're looking at how much of that gasoline is actually going to make the wheels turn. Well, it turns out that in most regular cars, your useful energy, that's what the car is using to make the wheels turn, is about 13 to 15%. There are a lot of losses in a car. For example, in the engine, here it says 62.4% of that energy is being lost. For example, we know engines get really hot. So there's thermal energy, there's heat that's being dissipated or wasted by the car. We'll try example 1 together. To heat up 1 liter of oil to 70 degrees Celsius, 3,400 joules are required in theory. To accomplish this task, your oven will need to consume 15,000 joules. What is your oven's energy efficiency? So we are looking for energy efficiency. We need to use the formula energy efficiency, EE, equals useful energy, EU, divided by consumed energy, EC, multiplied by 100 to get the percentage. In this problem, we have to read between the lines to find the values. First of all, here it says that it will consume 15,000 joules. So that's the value for EC. Consumed energy is 15,000 joules. And that's electrical energy. An oven runs on electrical energy. Now we still need useful energy, which is written up here. That's 3,400 joules required in theory. So that's the only energy needed to heat up some oil on that oven. Okay, so 3,400 joules of useful energy, which is thermal energy, because we need heat to heat up the oil. So it means, in theory, it just needs that much energy, but the oven needs to consume a lot more to get the job done. So it's not very efficient. Let's see how efficient it is. So energy efficiency is useful 3,400 joules, okay, divided by 15,000 joules, multiplied by 100, and your energy efficiency is therefore 22.7%. So that oven is only 22.7% energy efficient. We will try the other examples in class together.